Hello number theorists, and welcome back after this long break to our course about number theory and cryptography. We've seen in previous lectures that congruences behave very well for addition and multiplication, which means that if A is congruent to B modulo a certain integer n, and C is congruent to D modulo the same integer n, then one can deduce that A plus C is congruent to B plus D modulo n, and that A times C is also congruent to B times D modulo n. Now what we'd like to do is to see whether congruences, which means this sign here, really behaves like a real equality. For instance, we know that in the real world, if A times B is equal to A times C, and if A is different from 0, then one can deduce that B is equal to C, and what we've done here is to cancel actually both of the A's. This holds obviously because what we've done here is to put that AB minus AC is equal to 0, which implies by factoring by A that A times B minus C is equal to 0, and since A is different from 0, one can deduce that B minus C is equal to 0, which means that B is equal to C. Now, is this true for congruences? Things are actually a little bit more subtle than for real equalities, and we will see how. The main property that we used here to conclude that B is equal to C is the fact that if A times B is equal to 0, then either A is equal to 0 or B is equal to 0. This is true for classical algebra that one knows from high school, but it is wrong in general. For instance, if you take a 6-hour clock, we see that 2 times 3 is congruent to 6 modulo 6, which means it is congruent to 0 modulo 6, and thus 2 times 3 is equal to 0. Actually, it is congruent to 0 modulo 6, while neither 2 is congruent to 0 modulo 6, nor 3 actually is congruent to 0 modulo 6. So we see that congruences behave very well for addition and multiplication, but would not behave very well for cancellation. What we would like to investigate here is if AB is congruent to AC modulo a certain integer n, when can we deduce that B is congruent to C modulo n? Which means when can one simplify both sides by A? And we call this property the cancellation property. Let us see how things work on a concrete example. One can check that 2 times 7 is congruent to 2 times 3 modulo 8, and this is actually because 14 is the same thing as 6 modulo 8. But from this we cannot cancel both of the 2's because this would give that 7 is congruent to 3 modulo 8, which does not hold. See, so we cannot just simplify like in the real world, and one has to pay more attention to this. Moreover, one can check that 5 times 3 is congruent to 5 times 11 modulo 8, and this is because 15 is congruent to 55 modulo 8, because both of them is congruent to 7 modulo 8. Here 55 we can write it as 48 plus 7, which gives of course 7 modulo 8. We can also see that here one can cancel both of the 5's and get that 3 is congruent to 11 modulo 8. So things does not work here, but they work here. What we would like to investigate together is when does this work. We prove in what follows if AX is congruent to AY modulo n, and if the GCD of A and n is equal to 1. Let me remind you, GCD means the greatest common divisor of A and n. Then one can cancel both of the A's here and here to get that X is congruent to Y modulo n. In fact, we will prove something a little bit more general, namely if AX is congruent to AY modulo n, then one can deduce that X is congruent to Y modulo this time n all divided by the GCD of A and n, which means that if the GCD of A and n is equal to 1, one gets this result. This is actually a straightforward proof because if AX is congruent to AY modulo n, one gets that AX minus AY is congruent to 0 modulo n, or equivalently A times X minus Y is congruent to 0 modulo n, and this means actually that n must divide A times X minus Y. Now if we denote D the GCD of A and n, one can write A as d times a certain integer a prime and n as d times another integer n prime. Now, because d is the greatest common divisor of a and n, this means that a prime and n prime does not share any divisor except 1, which means that the GCD of a prime and n prime is equal to 1. Now we go back to our claim here, and one can write that a times x minus y is equal to n times a certain integer k, and this is because n divides a times x minus y. And if we replace a and n by d times a prime and d times n prime, one gets that d times a prime all times x minus y is equal to d times n prime all times k. We can cancel both of the d's, of course, and get that a prime times x minus y is equal to n prime times k. This means that n prime divides a prime times x minus y, which by the Gaussian lemma implies that n prime must divide x minus y. But n prime is actually n divided by the GCD of a and n, so it means that n divided by d must divide x minus y, in which case this means that x is congruent to y modulo n divided by d. And this is actually our result here. Let me remind you that this holds because the GCD of n prime and a prime is equal to 1, and that this is the Gaussian lemma. Bingo. Now, this cancellation property of congruences has many interesting consequences. One of those, if n is a prime number, then we know that if a is not congruent to 0 modulo n, meaning if n does not divide a, then the GCD of a and n must be equal to 1. So this means that if ax is congruent to ay modulo n, and moreover if a is not congruent to 0 modulo n, then one can conclude that x is always congruent to y modulo n. This is very nice because this looks like the real world actually. In the real world, if ax is equal to ay, and if a is different from 0, then one can say that x is equal to y. This means that if we have a clock of n hours and n is a prime number, then one can do the cancellations, but not only actually the cancellations, because we also have that if AB is congruent to 0 modulo n, and moreover if A is not congruent to 0 modulo n, then one can say that B must be congruent to 0 modulo n. And this looks like if AB is equal to 0, then either A is equal to 0 or B is equal to 0. One can prove this actually very easily because AB congruent to 0 modulo n is the same thing as AB is congruent to a times 0 modulo n. So if a is not congruent to 0 modulo n, which means that the GCD of a and n is equal to 1 if n is a prime number, one can deduce that b must be congruent to 0 modulo n, which means that we can cancel both of the a's here. Very nice, right? Let us see how this works on a concrete example. We would like to solve the equation x squared is congruent to 4 modulo 7. So 7 here is a prime number, and we've seen that congruences modulo a prime number has interesting properties. Now obviously 2 squared is congruent to 4 modulo 7, which means that 2 is a solution to our equation here. But does there exist any other solution? The answer is yes, and to find this solution one could use brute force, which means try all the values modulo 7 and see which one give us 4 modulo 7. So if x is congruent to 0 modulo 7, things does not work because x squared will be congruent to 0 modulo 7 as well. If x is congruent to 1 modulo 7, same thing, x squared is congruent to 1 modulo 7. Now if x is congruent to 2 modulo 7, we've seen together that x squared will be congruent to 2 squared, which is 4 modulo 7, and this is the first solution. And now if x is congruent to 3 modulo 7, one gets that x squared is congruent to 9 modulo 7, which is the same thing as 2 modulo 7, and this is different from 4 modulo 7. So 3 is not a solution. Now if x is congruent congruent to 4 modulo 7, then x squared will be congruent to 16 modulo 7, and 16 modulo 7 is the same thing as 2 modulo 7, which is not a solution here. Now, if x is congruent to 5 modulo 7, then x squared is congruent to 25 modulo 7, and 25 modulo 7 is actually 4 modulo 7. Bingo! This is the second solution, which means that 5 is a solution to our equation x squared is congruent to 4 modulo 7. Now, a last one is x is congruent to 6 modulo 7, and we will see that this does not work because actually equations of the second degree in congruences might behave like equations of second degree in the real world, and I insist on the might thing. Okay, so one gets here that x squared must be congruent to 36 modulo 7, and 36 modulo 7 is the same thing as 1 modulo 7, which means that 6 cannot be a solution to x squared congruent to 4 modulo 7. So this was brute force, which means that we tried all the different values of x to see which one gets us to 4 modulo 7. But imagine we would like to solve x squared is congruent, for instance, to 16 modulo 53, which is a prime number as well. It would be very tedious to do a brute force, at least by hand without a computer, and to check all the values from 0 to 52 and see which one gets us to 16 modulo 53. Of course, 4 is a solution, but there exists actually a second one. So how can we use our cancellation properties in order to solve such equations? Indeed, this equation here is equivalent to x squared minus 4 squared is congruent to 0 modulo 53, which is equivalent to x minus 4 all times x plus 4 is congruent to 0 modulo 53, and I used here that a squared minus b squared is equal to a minus b all times a plus b, which holds actually in congruences as well. Now that we know that if here we have a prime number, then a times b here is congruent to 0 means either a is congruent to 0 or b is congruent to 0. So we get here that either x minus 4 is congruent to 0 modulo 53 or x plus 4 is congruent to 0 modulo 53. This means either x is congruent to 4 modulo 53 or actually x is congruent to minus 4 modulo 53. Bingo! So the second solution here is congruent to 49 modulo 53. For those who are skeptical, you could check that 49 all squared gives actually 16 modulo 53. Okay, so you square 49, do the division modulo 53, and you will get 16 as a remainder. Actually, we could do the same thing here for this equation, and one gets that x minus 2 all times x plus 2 is congruent to 0 modulo 7, which gives either x is congruent to 2 modulo 7 or x is actually congruent to minus 2 modulo 7, and minus 2 modulo 7 is the same thing, bingo, as 5 modulo 7, and we've seen together that 5 modulo 7 is the second solution to x squared congruent to 4 modulo 7. This means actually that 2 and minus 2 are both solutions, but not only this, it means that they are the only solutions to x squared is congruent to 4 modulo 7, and it is the same thing here. We can see that 4 and 49 are the only solutions to x squared congruent to 16 modulo 53, and so it is useless to check other values of x to see whether they give 16 or not. We know from here that we only have 2 such solutions. Do you see how powerful cancellation is? So if you are in front of such equation, do not do brute force, please. It is better and more elegant to use the properties of congruences. We would like now to investigate how to solve linear congruences. Namely, if we have ax plus b is congruent to 0 modulo a certain integer n, in which x is the unknown, how can we solve such equations? Let me remind you that in the real world, if we have ax plus b is equal to 0, all we have to do is to say that ax is equal to minus b, which means actually that ax plus b minus b is equal to 0 minus minus b, and this cancels actually the b here. So we get that ax is equal to minus b, and then if a is different from 0, of course, one gets that the solution to this is x equals minus b divided by a. So can we do the same thing here? Actually, yes, we can say that ax is congruent to minus b modulo n, but the difference here, what does it mean to divide by a? Since we do not know what division means in the congruences, but we know what multiplication means, what we would like to do is to get rid of the a here, and to do so, one can multiply all of this by a certain a prime such that a prime x would be congruent to minus a prime b modulo n, and if you would like to get rid of the a, this must give us 1 modulo n. So if this is 1 modulo n, one gets rid of a, and we get x is congruent to minus a prime b all modulo n. Now the natural question is, does there exist all the time an a prime such that a prime times a is congruent to 1 modulo n? This is not true in general, as we shall see together. But in case this is true, we say that a is invertible and its inverse is a prime. And even in the real world, this is what we call the inverse of a, and which we denote 1 over a. It is actually the number that multiplies a, give us 1 here. It is the same definition here. If we would like to get rid of the a here, one possibility is to invert the a that we have here, which means to multiply it by a certain real number 1 over a, and this real number actually exists. With congruences, things are slightly different, and a certain a prime, which is 1 over a, does not always exist. Let us see how things work on a concrete example. We would like to know whether we can solve 2x is congruent to 1 modulo 7, which means does there exist an x such that 2 times x gives 1 modulo 7. This also means, is 2 an invertible number modulo 7? Does it have an inverse? It's the same thing as this one here, right? Well, to see whether 2 is invertible or not, which means whether this equation has solution, one could use brute force. Now if x is congruent to 0, nothing happens because 2 times 0 never gives 1 modulo 7. If x is congruent to 1 modulo 7, 2 times 1 does not give 1 modulo 7 because it gives 2 modulo 7. If x is congruent to 2 modulo 7, then 2x is congruent to 4 modulo 7, which is different from 1 modulo 7. Now if x is congruent to 3 modulo 7, then one gets that 2x is congruent to 6 modulo 7, which is still different from 1 modulo 7. Now if x is congruent to 4 modulo 7, then 2x is congruent to 8 modulo 7, and bingo, 8 modulo 7 is actually 1 modulo 7. So we see here that x equals to 4, or in other terms, x congruent to 4 modulo 7 is a solution to 2x congruent to 1 modulo 7. Is there another solution modulo 7 to this? The answer is no, and this is because if x is congruent to 5 modulo 7, one gets that 2x is congruent to 10 modulo 7, and 10 modulo 7 is actually 3 modulo 7, and this is different from 1 modulo 7. I'll leave it to you to check that x congruent to 6 modulo 7 is not a solution to 2x congruent to 1 modulo 7. So the only solution to this equation is x congruent to 4 modulo 7. So this means that 2 is invertible modulo 7 and its inverse is 4 modulo 7. And now for instance, if you would like to solve the equation 2x is congruent to 3 modulo 7, all we have to do is to get rid of the 2. And to get rid of the 2 here, we multiply 2 by 4, so we get 4 times 2x is congruent to 4 times 3 modulo 7. But 4 times 2 modulo 7 is the same thing actually as 1, so we get that 1 times x is congruent to 12 modulo 7, and 12 modulo 7 is 5 modulo 7, which means that x is congruent to 5 modulo 7. And this is the solution to our equation 2x is congruent to 3 modulo 7. You can check this by yourself because 2 times 5 gives actually 10, and 10 is 3 modulo 7. Bingo. Let us now check one more example. We would like to solve 2x is congruent to 1 modulo 6 this time. This also means, is 2 invertible modulo 6? Is there an x such that 2 times x gives 1? Actually, we can do this with brute force, and we know that if x is congruent to 0 modulo 6, then 2x is also congruent to 2 times 0, which gives 0 modulo 6. Now, if x is congruent to 1 modulo 6, 2x gives 2 times 1 modulo 6, which is 2 modulo 6, and this is different from 1 modulo 6. If x is now congruent to 2 modulo 6, then 2x is congruent to 2 times 2 modulo 6, which is 4 modulo 6, and this is different still from 1 modulo 6. Now, if x is congruent to 3 modulo 6, one gets that 2x is congruent to 2 times 3, which is 6 modulo 6, and 6 modulo 6 is 0 modulo 6, different from 1 still. Now, if x is congruent to 4 modulo 6, we will get 2 actually. You'll see that 2x is congruent to 8 modulo 6, and 8 modulo 6 is 2 modulo 6, and this is different from 1 modulo 6. And now, finally, if x is congruent to 5 modulo 6, we will get that 2x is congruent to 4 modulo 6, and this is actually cyclic because 2 times x is congruent to 2 times 5 modulo 6, which is 10 modulo 6, and 10 modulo 6 is the same thing as 4 modulo 6. So in all cases, 2x never hits 1 modulo 6, and which means that this equation does not have any solution modulo 6, or equivalently, 2 is not invertible modulo 6. So what we see here is that in the real world, every real number which is different from 0 has an inverse, which means has a number which we denote 1 over a, that times a gives 1. But in the congruences world, this is not enough, because we see here that 2 is different from 0 modulo 6, but still there does not exist any number of the form 1 over a in the congruences world such that this number times a gives a 1. So no number here, x times 2, can hit a 1. So what we would like to investigate here, more generally, on which condition ax is congruent to b modulo n has any solution. Of course, on which condition on a, on b, and on n such equation can be solved. Indeed, ax is congruent to b modulo n if and only if there exists an integer k such that ax is equal to b plus n times this k. In other terms, if and only if there exists this integer k such that ax minus nk is equal to b, and this is true if and only if the line L of equation ax plus ny equals to b has an integral point on it. But we've seen in a previous lecture that such a line has an integral point on it if and only if the GCD of a and n divides the number b. So in order to solve this equation, it is sufficient to solve this one here, and we've seen in previous lecture that the extended Euclidean algorithm is a very efficient tool to find an integral point on a line L such that the GCD of a and n divides the number b. So let us see how this works on a concrete example. We would like to solve the equation 21x is congruent to 14 modulo 35. The first thing to do here is to find by the Euclidean algorithm the GCD of 21 and 35, and we know that 35 is equal to 21 times 1 plus 14. We also know that 21 is equal to 14 times 1 plus 7, and that 14 is equal to 7 times 2 plus 0. This means that 7 is the GCD of 21 and 35, and this is actually obvious without the Euclidean algorithm, but we will need the Euclidean algorithm to find how to express 7 as a linear combination of 35 and 21. From this equality here, one can deduce that 7 is equal to 21 minus 14 times 1, and from this one here, we know that 7 is equal to 21 minus 35 minus 21 times 1, which is 14 actually, all times 1, which give us 21 times 2 minus 35 times 1. Does this really give 7? Actually yes, because 21 times 2 is 42, and 42 minus 35 is actually equal to 7. In the congruence world, this means that 21 times 2 is congruent to 7 modulo 35, and if you would like to get 14, all you have to do is to multiply both sides by 2, and we get that 21 times 2 all times 2 is congruent to 7 times 2 modulo 35, which means that 21 times 4 is congruent to 14 modulo 35, and this actually says that x congruent to 4 modulo 35 is the solution to our equation 21x congruent to 14 modulo 35. Actually, x congruent to 4 modulo 35 is not the only solution to our equation here, and there are exactly 7 solutions to this, which is the GCD of 21 and 35. To find the other solutions modulo 35, let us get back to the equality 7 is equal to 21 times 2 minus 35 times 1. This yields that 14 is equal to 21 times 4 minus 35 times 2 by multiplying both sides by 2, from which one can see that 4 minus 2 is a solution to the equation 14 is equal to 21x plus 35y, or equivalently 4 minus 2 is an integral point on the line of equation 14 is equal to 21x plus 35y. In order to find all these solutions to this, let us find all the integral points on this line. Indeed, if you subtract this equation to this one here, one gets that 21 times x minus 4 plus 35 times y plus 2 is equal to 0. This is because 14 minus 14 is equal to 0, from which one can deduce that 35 times y plus 2 is equal to 21 times 4 minus x, and if you divide both sides by 7, one gets that 5 times y plus 2 is equal to 3 times 4 minus x, which means that 5 must divide 3 times 4 minus x, and by the Gasser lemma, we can deduce that 5 divides 4 minus x, and this is because 5 and 3 do not share any common divisor except 1, and this means that 4 minus x is of the form 5k, or equivalently, if I write things down here, that x must be congruent to 4 modulo 5. So if x is a solution to this, then x must be congruent to 4 modulo 5, which means that the solutions to this equation here are x congruent to 4, or x congruent to 4 plus 5, which is 9, or x congruent to 9 plus 5, which is 14, or 19, or 24, 29, and finally 34. We can see here that we have exactly 7 solutions to our equation 21x congruent to 14 modulo 35, and this is because the GCD of 21 and 35 is equal to 7, and more generally, if ax is congruent to b modulo n, then the number of solutions to this, if there does exist a solution, is the GCD of a and n, and I'll leave it to you to see why. Now, if you are skeptical, you could check by yourself that 21 times 9, for instance, is congruent actually to 14 modulo 35. Bingo. Our exciting lecture ends here, and we will see together more about congruences in future lectures. Thank you for listening.